Hello students. In this lesson we are going to derive an equation for motion of variable mass. In the previous class we discussed the fundamental quantity of the matter mass and the difference between mass, fundamental quantity of the mass, that is matter, and the variable mass. Fundamental quantity of the matter that we call as mass, it is constant anywhere at any time. There will be no change in its quantity and it is measured in kgs and grams and pounds. And mass is the fundamental quantity which does not depend upon any other physical quantity. But here, what is this? Variable mass. So this is the variable mass which varies with respect to time. We already discussed this point in the previous class. So this mass varies. How does it change with respect to time? Whether it is increased or decreased. Maybe any case, it may be increased or decreased. And I also told you that if this system, variable mass system, gains some mass after some time, so it means some mass, a small amount of the mass is added to the system, then added mass is considered as positive, or else after a very small interval of time, if an amount of mass is ejected out, it comes out from the system, then it is considered as negative. So in this lesson, we will derive an expression for the motion of this variable mass, and this expression consists the velocity of the system as well as the velocity of the mass which is ejected out. So to derive this equation, we consider that a small amount of mass ejects out from the system. We are not adding the mass, but a mass is ejected out. So the ejected mass, obviously it is negative. It is considered as negative. And in this lesson, while deriving this equation, we use Newton's second law of motion F equals to ma also. So let us start deriving equation of the variable mass. So we start with a system. That system, it is moving. So it is moving means it has certain velocity. So that system is, we denote like this. And it is moving with velocity. And this velocity, we denote this velocity here in this direction of the velocity, from left to right. And also we represent the velocity with the velocity and the mass. Mass is also there here. So, and mass equals to here m. So this is the system, original system. And this original system, it is in motion. Now, it has momentum as it is in motion. So momentum, I will write this momentum of this motion here. P, momentum is denoted by P, so we denote with P, which equals to product of mass and velocity, so mv, product of mass and velocity. So if you write like this, so the system moving with the velocity and after some time, some amount of mass is ejected out. This is a reaction. We consider that this is a reaction. So before the reaction, the momentum of the system is mv. So I will write this is equals to P1. P1 is the momentum of the system before the reaction. And after some time, very small interval of time. So after time dt, I denote with the dt. So this is the time here. So after time dt, a very small amount of the mass is ejected out. So ejected mass we denote with dm. Sorry, this is dm. So when this mass is coming out, and what is its state, whether it is at rest or in motion, we have to consider that one also. So we consider that this ejected mass is also moving, then we have to represent the direction of this ejected mass also. So this is the reaction. After this reaction, what is the remaining mass in this system? So this is the system here. So in this system, a small amount of the mass has come out in time dt, then the remaining will be m minus dm. Now we have to consider that one also here. This is the mass which is remained here. So the remaining mass, it is here m minus dm. This is the remaining mass. And what is the direction of this remaining mass? Direction of this remaining mass, this is the same direction as before the reaction. So in the same direction it is moving here. So when it is moving in the same direction here, and we have to mention the direction of this velocity also, but mass is reduced. We know that small masses have large velocity. So here also the system lost some mass. So obviously velocity increases. So we have to write down what is the velocity here. Currently, what is the velocity of this system? So velocity, this one for this system will be, already it has v plus an amount of velocity is increased. This is increase in the velocity. So this is the velocity of the system, remaining mass of the system moving in the same direction as before. And then, so what about this dm? So this is the mass dm which is ejected out. So this mass, it is moving in opposite direction. So it is moving in an opposite direction. We will mention like this. So this is the direction of the remaining mass, sorry, ejected mass. And we have to represent the ejected mass also. So this is the ejected mass here. So that is the ejected mass. So, and then what is the velocity of this ejected mass? We have to note down that. So then this is moving in this direction and ejected mass is very small. So this is the small mass here, and we have to represent the small mass also as dm, and we have to represent the velocity also for that. So the velocity of that one, it is in this, which direction we have to see. So this is the direction of the velocity of dm, and we represent the velocity of dm, small mass ejected out, with u. But this mass dm which is ejected out from the system is moving in opposite direction to the original system. So we will put a negative sign for that. So minus u. Why negative sign here? Because dm, small mass dm, it is moving in opposite direction to the original mass. So this is the reaction here. So before the reaction, the total mass of the system is m, and velocity v, mass is m, momentum is p1 here. And after some time dt, the reaction is here. Here we have the reaction here. So this is the ejected mass, and this is the ejected mass dm, and this is u is the velocity of the dm, and in opposite direction this is right to left, and the remaining mass is from left to right. So this is about the reaction. Okay, this is the phenomenon. Now we are going to derive the equation for this phenomenon, for this reaction. So here we have mentioned this one, momentum equals to P1 into mv before the reaction. Then we have to write the momentum. We have to express the momentum after the reaction. So what is the after the reaction? We have to write that. So this is the momentum after the reaction. Momentum. So momentum, this is actually there are two bodies here. Before the reaction, only one body. Now we have two bodies here. Momentum P2. I'll write it as P2 because this is after the reaction. So momentum, right, I'll write P2. This equals to here. So momentum, this is of dm. So what is that dm here? So this is dm here. So we have to write the momentum of the dm and plus momentum of m minus dm plus momentum of m minus dm. So there are two quantities for P2 here. So then accordingly we have to write here. So P2. So this is P2, we are writing here momentum of dm, this is minus u into dm. So minus u, I'll write it as a star, I'll put a star here, not to be confused, dm plus momentum of m minus dm. So mass is m minus dm and multiplied by v plus dv. So this is the final momentum here. So here we have two momentum. One is before the reaction and another is after the reaction here. Now, why this momentum is changed? Why there is a mass ejected out from the system? So we have to observe that. So to derive the expression here, so we have to study this case with respect to the external force. There is an external force acting on the system, this m. So when an external force is acting here, then an amount of the mass has come out here. So now we are going to write the amount of external force, magnitude of external force according to the Newton's second law of formula. So we use the Newton's second law and then we will write the external force here. So external force F equals to, so this is MA according to Newton's second law, and this is also written as dP by dt, that is the change in momentum per unit time. So we can write it as P2 minus P1 divided by dt. We can write like this also. So we use Newton's second law for deriving that. And this force. So this force here, this is the force which is according to Newton's second law, it is the external force. This is the external force acting on the system here. And this is the mass and acceleration. This is the general equation here. So this general equation can be written in this form here. Now we substitute P2 and P1 values to derive that equation here. So when you substitute that one, so left hand side is F equals to here, I'll write P2 first. So this is P2. So this is P2 here. P2 equals to minus U dm plus m minus dm into v plus dv. I'll write first that one. So if I write that one here, this will be minus u into dm plus m minus dm multiplied by v plus dv. So this is P2 value. And again we have the P1. What is P1? So P1 equals to mv. Here we have P1 here. So and minus, so P1 is mv and whole divided by, so this is whole divided by dt. So we have to write dt. So this is the equation for So let me write once again here. So this is minus u dm plus m minus dm multiplied by, this is v plus dv and minus initial momentum is mv. So this is divided by the total term is divided by dt. Yeah. So we divide the total term with dt. The next step here we have two terms m minus dm and v plus dv. We expand these two terms here. So when you expand these two terms here, we will have, and this is the equation here we have here. So this is f, left hand side as it is, equals to minus u dm, I'll write as it is, plus this m into v, mv, and plus m into dv, I'll write m into dv, and this here we have minus dm multiplied by v. So minus, I'll write first v minus dm, let it be, multiplied by v and minus dm multiplied by dv. Here we have. So minus dm multiplied by dv and minus mv. This is the initial momentum, and again this is whole divided by dt. Here. So okay. Here we have two terms to be cancelled here. So those two terms are here. We have two terms. One is here mv plus mv and another is minus mv. So this plus mv and minus mv will be cancelled here. And what about the remaining here? So we have the remaining terms here. So this is f equals to minus u dm plus m dv. Here we have minus dm into v, but this is the v velocity of the original system. So that is the larger one, that is the initial one. And dm is a small amount, very small amount. Comparing with the system, original system, this mass, the value of this dm is very small and also ejected out. So this will be negative. So this will be negative means minus, I'll put that as minus dm. First I'll write minus dm and then we can add it here. And then minus dm into d. And then here whole divided by dt here. So again here we divide the whole term with dt. So whole divided by dt. So these are the remaining terms here. So when you do this one here, this is a minus multiplied by minus, you will have plus. So here we have minus sign and a negative sign either also. So both are multiplied here plus you will have. So now we will write the next step as here. This is here equals to minus. So we start with the open bracket minus u dm plus m dv, and this will be plus dm multiplied by v, I'll write like this, and then minus dm into dv. So this will be dm multiplied by d and whole divided by again d. So we divide the complete term with dt. So next step here, what's the next step here? Here we have a common factor. First, we separate each term. So each term is separated here. F equals to, first term is minus u dm by dt. Second term, first I'll write v, then multiplied by dm by dt. And third term is, here we have minus dm multiplied by dv by dt. So this is about that one. And we have one more term also here. So this is m dv by dt. Here we have that one also. So that one is, I'll write in the last, plus m dv by dt. This is the last step. So the next step, in the next step, here we have again take a common factor, dm by dt is common factor in these two terms. So I will take a common factor here. So this will be f equals to v minus u. So this is multiplied by dm by dt. And these two terms are combined. Next term is minus dm multiplied by dv by dt here. And the last term is here. This is the last term in this expression. So m dv by dt. So this is the last term here. So next, the next consideration here. So this is the middle term. What the middle term we have here? So this is the middle term. So this middle term, this one here. So this is the term. This is dv by dt. This is the change in velocity with respect to this is change in velocity with respect to dm. So as dm is very small, with respect to dm, there will be no such a large change in the velocity of the system. The system is very large comparing with dm. So even the velocity of the system is also very large comparing with the velocity of the dm. So we can neglect this term dv by dt. It is 0. The change in velocity of the system, this one. So this is, so we can put it as, so this is equal to 0. So we can put it as 0. So this value, so this is equals to 0. So we can neglect this term. So when you neglect this term here, the remaining terms will be here. We have F, this is external force, equals to, so this is V minus U multiplied by dm by dt. And this is cancelled. So this is 0. We don't consider now. Now the remaining last term is m dv by dt. So this is the last equation. And this equation here, this is the expression for variable mass system. In this equation, we have two terms on the right hand side, v minus u dm by dt. So v minus u, this is the relative velocity. And with respect to this mass dm of the system. So this term v minus u multiplied by dm by dt, this is called the third acting on that one. So then m dv by dt, this one. This is f external here. So we can write it as here f external. So I can write it as external This equals to, first I will write m dv by dt and then plus v minus u into dm by dt. So this is the required equation for the motion of variable mass here. So in this equation we have the external force which is equals to a thrust of the system, thrust acting on the system, and plus m dv by dt. This is the force applied on the system here. This is the acceleration. dv by dt is the acceleration of mass m. So this is the final equation. Okay. So this is about the motion of the variable mass. In the next lesson, we are going to derive an equation for the velocity of rocket system. Rocket system is also an example for variable mass. A simple difference is there. So in the next class, we will derive the velocity for rocket system. Okay.